Hello everyone. Today we're going to solve question number 61, rotate list. Given the head of a linked list, rotate the list to the right by k places. Okay. So in this video, I'm going to discuss two methods to solve this question. Okay. This is a function that I have already kept with me. That is going to be a getLength function, which calculates the number of elements inside a linked list. Okay. So it's just a simple function where we pass a head of the list. It will calculate how many elements it has using a counter, and it will return the number of elements. Okay. This function is going to be used in both of these methods. Okay. So I've separated it. Okay. Next, you can see the question here is, let's see here. Okay. So the question here is, you can see, let's say for this list, we have value k is equal to 2. Okay. So in that case, since we have k is equal to 2, you can see for first rotation, the last element comes and attached to this place. For second rotation, this last element comes unattached to the head position. Okay. So this is the way in which we are rotating our element for k times. Okay. So this is majorly the goal of the question. Now, here are some insights on this question. Okay. First thing that you can notice is if number of nodes equal k, in that case, there's no rotation is required. Okay. You can see here that if the number of k for this linked list is 5, in that case, 5 will reach again to the end of the list after 5 rotations. Okay. You can also see here that for this list, let's say the number of elements inside here are 3 and k is equal to 4. Hence, after 3 rotations, okay, since the number of nodes inside this list are 3, the rotation comes back to the original list. You can see this list rotation 3 and the original list is same. Okay, so we can smartly reduce our number of computations by so that they are less than the number of values inside the list. Okay, so that's one thing. Second thing, if k is equal to 0, then there's no rotation required. This is obvious. Third thing is, for k greater than length, we need to readjust it. Okay, so this is the readjustment part, where if list has a length of 5 and k is equal to 8, so after 5 rotations, list is going to come back to its original shape. Okay, hence we don't have to do 5 rotations before this. You can directly use 3 rotations to get a final answer. Okay, same as this one, where we don't have to do rotation 1 2 3 for because rotation 4 is equal to rotation 1, so after one rotation we finally got the answer. Okay, so these are the insights for this question. Let's study the methods to solve this question. The first method is going to be, you can see it, insert head for k times. Okay, so basically what we are going to do is we are going to calculate number of rotations required, then we are going to remove the tail element, and then we are going to insert it head. Okay, and this procedure is going to be done for k times the number of rotation that we calculated. Okay, so the tasks for this method are going to be calculate length, readjust k. Okay, the readjustment part is important so that we don't recompute the same rotations. Okay, calculate the length, and then after this we are going to recreate list or update existing one. Again, like, it's against the question that we can update the values directly. Rather, what you have to do is you have to like recreate, because you have to just pick this last element and put it in the correct position. Okay, third thing is going to be directly returning the answer. Okay, so let's see the visualization. It's going to be a short one, but let's complete this. So this is a list, and for this, k value of k is equal to 2. So what we are going to do is we are going to remove the last element, and then we are going to insert it at head. Okay, so it's going to look like this. After k is equal to 1, the list is going to be something like this. For in the same fashion, we can, for k is equal to 2, we can remove the last element. For this one, the last element was 5. For the current list, the last element is going to be 4. So we'll remove 4, we'll insert it at head, and this is our final answer. Okay, you can compare this. This is our final answer: 4 5 1 2 3. 4 5 1 2 3. Okay, so this is going to be our method. Okay, so let's code this one. What we need is, first we'll calculate the length. So int n is equal to get length. of head. Okay, so this is going to give us the length of the linked list. Now I'll put on some of the functions. Okay, so sorry, some of the base cases. So what I mean by base cases is while not head or not heads next. Okay, so these are the two conditions where uh, you can say the list need not to be rotated. Okay, the constraint gives us that the number of nodes inside this list can be 0 or 1. Okay, so if the number of elements are 0, in that case you can directly return head. If number of elements is 1, then also you can directly return head. Okay, so this sorts out some constraints, some edge cases. Next part is going to be readjustment of k. Okay, so since we have calculated n here, the n can be 0, so a is equal to k percent n. But since we have a head check here, hence we won't have a division by 0 error over here. Okay, next part is going to be so you can see what we have done is, if k was, let's say k was 8 and n was 5, now k is going to be 3. Okay, now k is going to be 3. Okay, we have readjusted k for our needs. So for the first method we'll need a loop. So int, I'm going to write it as times, because this is the number of times that I have to uh, pick the last element and insert it. Okay, times is equal to k. You can directly use k too, but I don't want to change the input that they have provided, although we have done it. Okay, so while times minus minus. Okay, so in this case what we need is we have to pick the last element. Okay, so list node star last is equal to head initially, then while last next is not equal to null. Okay, so this is going to help us reach the last element, or the last node. Last is equal to last next. Okay, now once we have reached the last element, we just need to adjust it to a correct position. Okay, so uh, what we need is, okay, one thing that we also needed was to disconnect it. We'll need a previous, so previous is equal to null pointer. Okay, and this is going to be previous is equal to last. Okay, you can see here, for disconnecting this list we'll need a pointer here, so hence I'm creating a previous pointer here, and I've reached the last pointer at this node. I've named it as last, and I'm going to disconnect this link, and then I'm going to put this link as the head of this original link. Okay, so now I have correct place of previous and last, so I'm going to disconnect. So previous next is equal to null. Okay, now I've disconnected it. Now the part comes where we have to reconnect to head. Okay, so last next is equal to head, and head is going to be updated to last. Okay, so this is the complete node. What this is doing is, you can see I have named this as last. Last next is going to be head, and head is going to be updated to this last. Okay, so this pattern is going to be followed for n minus n times, and in the end we have to return head. And since we are updating the value of head, there's no need for another li. Okay, so that should do it. Okay, let's submit this. So that's it for first method. Let's see the second method to solve this question. This method takes of n square time complexity, because we are finding the last element for k times, and k can be n minus 1. In that case, we have to travel n minus time and n minus 1 times for the last element of the node, which is almost equal to n. So n into n is n square. Okay, so that's it. Let's see the second method. So for the next method, what we are going to do is basically we are utilizing a trick where we are converting this list into a circular linked list. You can basically say it as circular linked list. Okay, although we are not actually creating it, but we are using the analogy where, just to reverse this list, what you can do is you can connect the last element with the head of the list, and then you can disconnect it at the correct position so that you can like get your final answer. Okay, I've kept some you can say some part of the code with me from the previous method. This is because these are very standard and works for both of these methods. Okay, basically we are calculating the number of elements inside the list. This is for this constraint part where we have 0 or 1 element. So this basically base case, and this is adjustment for k. This is for lower computations. Okay, can also do for k for all values of k, but it's wasted computation. Okay, so next thing that we can see is let's see the method how it actually works. Okay, so basically in the last method the issue was we have to reach the last element n number of times. Okay, this time what we're going to do is we are going to calculate the number of rotations required, and then we're going to reach a cutout point. Okay, after reaching a cutout point you can reconnect it to head. Okay, so basically what you're doing is, rather than putting each element to the head of the list, we are disconnecting a specific part that is required, and then we are connecting it at once. Okay, so by that we don't have to compute the last element n number of times. Okay, we just have to compute once what is our disconnect point. Okay, so the tasks to follow in this method are going to be, first you need to calculate the length of the list same as previous, and readjust the k. We have already done the step one. Okay, next step is going to be traverse to reach the split point. Okay, so let's say how you're going to reach the split point. Okay, so my core intuition was that the split point is going to be a point because after which is going to be the last node in the, or you can say the final answer. Okay, the last node in the final answer, which you can see here from our example, is going to be 3. Okay, so basically I have to reach 3. So to reach 3, you can see I have disconnected 2 elements from here, and there are total 5 elements. So my disconnect point basically becomes 5 minus 2, which is 3. Okay, so in this way we figured out that to calculate the exact number of nodes, we can directly calculate the length and subtract it with k. So basically n minus k, which is going to give us the disconnect point, and we can disconnect it and reconnect it to the head of the list. Okay, so you can see in this visualization part we have this original list, and we have this part, and we just have to combine them. Okay, that's the simple visualization and simple method that we're going to implement. Okay, there can also be other methods to solve this question where we can use array and other stuff, but I wanted to keep it to linked list itself. We have already discussed a lot of problems in which we use array in place of linked list. Array makes a lot of accessing easier, but since we are studying linked list, we can directly use a linked list for this problem. Okay, so what we'll need is, first, we'll need the disconnect point. Okay, we have already done task one. We need to reach the split point. So the name this as list node star. Can say previous because we generally disconnected using previous. Head. I'm going to name it as head. And so one thing that might work is if we index this using one based indexing. Okay, so for one based indexing, 1 2 3 4 5. Okay, so I have to reach this point. Okay, so for int I equal 1, I less than n minus k, I plus plus. Okay, so what is this giving me? Let's see. If I was 1 and n minus k is going to be 3, so this loop is going to run for 2 times. Okay, so this loop is going to run for 2 times. So I is equal to 1 and minus k is 3, so 1 and 2. Okay, so after 2 shifts you can see if it's at head 1 2, so for 2 shift we perfectly reach at 3. Okay, so next we'll need to move previous. So previous is equal to previous next. Okay. Next part, once we have reached the exact location, we need to store the future values. Okay. So list node star head to, I'm going to name it as head to is equal to previous next. Okay. And now what we'll need is previous next is equal to null point 2. Okay. Okay, one thing that we can also write here is one thing that I might have missed in previous method is going to be if k equals 0. In that case, you can directly return it. We have already discussed this inside over the section. You can see if k is equal to 0, there's no rotation required. I'm mentioning it here. Okay. Next part. Now we have this head to disconnected in this manner. We have head to this we have completed this part. Now we just have to reach this tail and connect it to head. Okay, so to reach to tail, list node star tail is equal to head to. Now while tails next is not equal to null, tail is equal to tails next, and then what we need is tails next is equal to head. Okay, the original head. Okay, so you can imagine that we are reconnecting this. We have reached this tail and we are connecting it to head, and now we have to update head. So we're gonna update head. This is reconnect, and this is each tail. Okay. Now we'll need head to, oh sorry, head is equal to head to, and return head. Okay, so this should work. Tails next is equal to head to, yeah, this should work. Let's run this. You can directly return head to, I guess, also that works too. This step is completely unnecessary, but yeah. So that's it. We have solved this question using um, like two approaches. This method takes offline time complexity because we just have to travel once and once to get length. So basically offline time complexity. So that's it for video. Thank you for watching.